Hello, welcome to another module in this massive open online course on estimation for wireless communications, correct. So far we have looked at a simple model of a wireless sensor network. We have formulated the likelihood function, and based on the likelihood function we have derived the maximum likelihood estimate of the unknown parameter. So far what we have done is we have considered a simple wireless sensor network, an example of a wireless, a scenario rather of a wireless sensor network. We have looked at n observations in this wireless sensor network. The observations are y1 equals h plus v1, y2 equals h plus v2, yn equals h plus vn, where these y1, y2, yn, these are our observations, right. H is the unknown, H is the unknown parameter, and these V1, V2, Vn, these are IID independent. So, V1, V2, Vn, these are IID, that is independent, identically distributed Gaussian noise samples with mean 0 and variance sigma square. These are IID Gaussian noise samples, all right. So, these are IID Gaussian noise samples with mean 0 and variance equal to sigma square. These are IID Gaussian noise samples with mean 0 and variance sigma square, and for this scenario we had derived the likelihood function. Yeah, we had derived the likelihood function for this scenario, and we have shown that the maximum likelihood estimate is given by the sample mean. The ML estimate, the maximum likelihood estimate or the ML estimate, that is h hat, the maximum likelihood estimate of the unknown parameter is basically 1 over n summation k equal to 1 to n y of k, that is this is the also known as the sample mean, or simply basically your average of observations y1, this is the sample mean, that is h hat, which is the maximum likelihood estimate. What is this? This is the ML estimate of your unknown, the ML estimate of the unknown parameter h, which is given by this average, that is 1 over n summation k equals 1 to n y of k, that is the average of the observations y1, y2, yn, or also basically the sample mean, that is the sample is y1, y2, yn, this is the mean or the average of the sample, therefore, this is also known as the sample mean. This is the maximum likelihood estimate for the simple scenario, simple wireless sensor network scenario with n observations that we have considered so far. of sensing an unknown parameter h, which we said can either be a parameter such as the temperature, pressure, the humidity, etc. Yeah. So, now let us examine the behavior or the properties of this maximum likelihood estimate. So, in starting this module, let us explore the properties let us explore the properties of the maximum likelihood estimate. Now, remember we have h hat equals 1 over n summation k equals 1 to n y k, and recall that each h k, each y k observation y k is random in nature. In fact, each y k is random Gaussian. If you remember the very first module, we had said that these y's y1, y2, yn are noisy observations with mean given by the unknown parameter h and variance given by the variance sigma square of the noise v k. Therefore, each y k, that is, it is important to stress this aspect, each y k is random in nature, in fact random Gaussian, which means h hat, which is the sample mean or average of these y k, is also random in nature. H hat, in fact h hat equals the average of these different observations y k. Your h hat is the average of these different observations y k. The y k is the observations, the noisy observations are themselves random in nature. Therefore, h hat is random, that is, the estimate is random in nature. That is the first thing that we have to realize, that is this estimate, the estimate h hat is random, that is, it is not a deterministic quantity, it is random in nature. Now, since h hat is random in nature, it is not necessary that it is equal to the true parameter h. Therefore, h hat is a random quantity, therefore, it is not always equal to the true parameter h. Therefore, h hat is not necessarily equal to, in fact, it is not necessarily equal to h. Therefore, the estimate, this is the estimate h hat is the estimate h is the true parameter, the underlying true parameter which is unknown, right. So, we have the estimate h hat which is derived from the observations, and then we have the true parameter, that is the original parameter h, which is unknown and which we are trying to measure, and what we are saying is h hat is random. Therefore, it is not necessary that h hat is actually equal to h, and so therefore, we want to find how good of an how good is this estimate h hat, what is the behavior of this estimate h hat, I mean what kind of properties does this estimate h hat exhibit, and how close it is to the true parameter h. Since it is not exactly equal to h, can we at least hope in some sense that it is close to the true parameter h. So, h hat is random. Therefore, what we want to do is we want to explore what is the behavior of h, or what is the behavior of h hat, and in some sense we want to explore, we want to address this important question, how close is h hat in what sense, how close is the estimate h hat to the true how close is this estimate h hat to the true parameter h. Now, in that sense, let us start by computing the mean let us start by computing the mean and variance of this estimate. So, to address this question, to address what is the behavior of this estimate h hat and also how close is this estimate h hat to the true value of the underlying parameter h, let us start by computing the mean and the variance of this random quantity of this estimate h hat, which is random in nature. For that, once again recall that h hat is the sample mean, h hat equals 1 over n summation k equals 1 to k. This is the sample mean. Observe that this is a linear combination of Gaussian random variables Gaussian random variables y1, y2 up to yn. Remember, we started in the very first module itself, we said that yk, each yk is Gaussian in nature, because the noise Vk is Gaussian in nature. You are shifting that by the constant mean, that is h. Therefore, each yk is also Gaussian in nature. And further, what we have is this estimate h hat, which is the sample mean. H hat is the sample mean. Therefore, h hat is a linear combination of these observations y1, y2 up to yk. Now, since h hat is a linear combination of these Gaussian random variables y1, y2, yk, h hat itself is Gaussian in nature, because the linear combination of Gaussian random variables is Gaussian itself. Since h hat is a linear combination of Gaussian random variables, h hat itself is Gaussian in nature. So, this h hat is Gaussian in nature, since it is a linear combination of Gaussian random variables. So, the first thing that we have established is that the maximum likelihood estimate h hat itself is a Gaussian random. It is a random variable, and in fact, it is a Gaussian random variable, since it is a linear combination of Gaussian random variables. Okay. So, h hat is Gaussian in nature. So, h hat is Gaussian in nature. Now, what is the mean of h hat? Now, what is the mean or the expected value of h hat? Now, recall for this, each yk is h plus vk. Yeah. And further we have, remember, we assumed the noise to be 0 means, that is, we have expected Vk, for each Vk we have expected Vk is 0. This is because the noise is 0 mean. Alright. So, we are going to use this property. Remember, in each observation Vk, in each noisy observation Vk, in each or noisy observation yk, the noise Vk has mean 0. Now, let us look at h hat. H hat is in fact 1 over n summation k equal to 1 to n yk. Now, substituting this expression for yk, remember, each yk is h plus Vk. So, this is summation k equal to 1 to n h plus Vk. which is equal to now divided by n. I have summation h plus V k, which is n times h plus summation k equals 1 to n V k, which can now be simplified as h plus summation 1 over n k equals 1 to n V k. This is my h hat. So, I have simplified this expression for h hat. H hat equals, that is the estimate. Remember, this is h hat, which is, let us not forget what these are. This is estimate h hat. This is the true parameter h, and these VKs, these are the noise, the observation noise, such that each expected VK equal to 0. Therefore, now if we look at the average value of the estimate h hat or the expected value of the estimate h hat, I have expected value of h hat is given as the expected value of the expression above, which is the expected value of h plus 1 over n summation k equal to 1 to n V k, which is equal to expected value of h plus expected value of 1 over n summation k equal to 1 to n V k. Now, look at this, this is a constant. So, expected value of h is basically h. So, this is equal to your h plus 1 over n summation k equals 1 to n expected value of each V k. Now, remember we said the noise is 0 mean. So, expected value of each V k equals 0. Therefore, net what we have is that basically your expected value of h hat, that is your the average value of the estimate, the expected value of h hat equals h, and this is a very important property. That is, even though what we are saying is that even though your estimate h hat is random in nature, that is h hat is not necessarily always equal to h. However, it exhibits a very important property, and the property that it exhibits is that on an average, that is if you look at expected value of h hat, that is the average of h hat is basically equal to the true parameter h, and this is a very important property of the estimate, that is it says that the mean of the estimate is equal to the true parameter h. This such an estimator is known, or such an estimate is known as an unbiased estimate. This is an important property. This says that basically the average value of the estimate, what does this signify? This signifies that average value of estimate equals true value of the parameter h. Therefore, such an estimator is known as an unbiased, that is it has no bias, that is no preference, it is an unbiased estimate or an unbiased it is known as such an estimator is basically known as an unbiased estimator. That is, it yields an unbiased estimate, which means even though it is random in nature, the average value of the estimate is basically equal to the true underlying parameter h, and therefore the ML estimate that we have derived is unbiased in nature. Let us also write that down, let us also note that down. Therefore, the ML estimate, or in other words our sample mean, that is the sample mean is unbiased in nature, yeah, which means that what do we have? We have expected value of h hat is equal to h. What is this? This is the average value of the estimate, and what is this? This is the true value of the underlying parameter. This is the true value of the underlying parameter, and what we are saying is, on an average, the average value of the estimate is equal to the true value of the underlying parameter. Therefore, the estimate, or therefore this maximum likelihood estimate is unbiased in nature, which is a very important property of the estimate. In fact, it is a very desirable property of the estimate. Yeah, so this unbiased property is a very important and desirable property of the estimate, which says that on an average, the average value or the mean of the estimate is equal to the true value of the underlying parameter. All right. So, in this module, what you will looked at is we have started characterizing the behavior of this ML estimate, yeah, which is basically for a simple sensor network with noisy observations of an underlying parameter. We have said that the maximum likelihood estimate is the sample mean of the observations, and we also deduced that even though this is random, in fact random Gaussian in nature, that is the estimate h hat is a Gaussian random variable, that is, it is not necessarily always equal to the true underlying parameter h. On an average, that is the expected value of this estimate or this estimator is equal to the true value of the underlying parameter h, and therefore, this maximum likelihood estimate is an unbiased estimate, which is an important property. So, we will stop this module here and continue with other properties in the subsequent modules. Thank you very much.